Hi friends, welcome. In this video I'm gonna introduce a simple and low noise linear power supply which you can see on the table. So let me show it up closely. This is a top view. You can see the heatsinks, power resistors, and the input and output connector. And this is the bottom view. Focus. Alright, this is the bottom view of the PCB board, and pretty much that's it. All component packages are through hole, so pretty easy to solder and build this device. As you know, linear power supplies have two main advantages. The first is better line and load regulation figures, and the second is lower noise and ripple, especially in higher output currents. Alright, you would also need two 5K potentiometers. I have used these cheap ordinary ones. However, I suggest you to use high quality multi-turn potentiometers. Now let me connect the potentiometers to the board using the XH connectors. So let me connect this second potentiometer. There we go, and show it up closely. Alright, two 3-pins XH connectors for two potentiometers. I will also connect this 4.7K resistor at the output. This is a simple light load that would draw a few milliamperes of current. It is necessary for testing purposes. It will make the output stable. It's a basic load. Turning, and it attached to the output terminal. There we go. The next thing I should do is to connect these two thick wires to the input terminal, and then these two wires would be connected to the power supply. This is the ground one, and this one is the positive. Okay, let me make these connections. Turning. It's done. This is a ground wire, and this is the supply wire, okay, or power wire. I used the Siglent SDM3045X multimeter and Siglent SDS2102X Plus oscilloscope for testing. The first thing is I did was to increase the supply around its maximum. So I think it is around 29 volts. Let's measure the output voltage. We can say under no load. This is the maximum voltage. The potentiometer was on its maximum level. So let me show you the minimum level. As you can see on the multimeter screen, 1.28 volts is the minimum voltage that you can get out of this power supply. Now I increase it slowly. 9 volts, 10 volts. Let's see how much it goes. Okay, I think it at least we can get 27 volts. I will measure the supply voltage also and see. I will show you how much is the difference between input and output voltage. Alright, 27.35 is the maximum voltage. Out of how much? Let's measure the input voltage. So input is 28.9. So the difference is around 1.6, between 1.6 and 1.7 volts. So this is the voltage that you should consider, the difference between input and output voltages. Alright, so far so good. In this stage I will show you how the current limit feature works. Let me decrease the output voltage to around something 13 is okay, 13 volts for the output, and then decrease the input voltage to prevent the regulator from overheating. Let's measure the input voltage. It's around 16.7 volts. Alright, the next thing I'm gonna do is to set the multimeter to measure the current. For this purpose, I should disconnect the red probe and put it on the current measurement input. This input is for the current measurement. Then I should set the multimeter, pressing the shift and this one, and that's it. Now the multimeter is ready. Okay, now what should I do is to put the multimeter probes on the output terminal. And there we go, it's high. Let me put it on the minimum, and thank you very much. 1.1 milliamp is the lowest current that we can set on this device. Okay, let me increase it. It is much easier if you use a multi-10 potentiometer, as I said before. So it goes to 1 amp, 1.7, 8, 2, 2.4, 5, 8, 3. Okay, we reached to the limit of the power supply. I should decrease the current because the voltage also dropped on the power supply. Anyway, my power supply cannot go higher than 3 amps. Let me decrease the current limit and set it on something around 300 milliamps. Like this. As you know, when I put the probes like that, it means I have shorted out the output terminals. It means the output current will never go higher than 300 milliamps in this case. This circuit can tolerate up to 4 amps. However, you should think about using bigger heatsink and proper ventilation. Alright, now we reach to the part which I'm sure you are interested in. That is the output noise measurement using the oscilloscope. As you can see on the table, I will use the SDS2000X Plus oscilloscope. So the first thing I'm gonna do is to prepare the probe. Therefore, I'm gonna remove the probe tip and then disconnect the ground lead and replace the ground lead with the ground spring. Okay, let me find the ground spring in the bag. Everything is provided in this plastic bag with the probe. It's here. Come on, come on, come on. Yeah. Okay, there we go. Then put the ground spring on the probe's tip, like this. Let me show it up closely, if the camera gets focus. Hello? Get focus. Get up, man, it's morning. Focus. Alright, this is how your probe should look like. Alright, my plan is to test the output ripple and noise in 2 steps. First, without any output load, and the second, I will put a load at the output that can draw around 1 amp or something. So let's test the output noise under no load, play with the volts division and put it at the 5 millivolts per division. This is the lowest for the times 10 probe. I see some high frequency noises, which still I don't believe belongs to the power supply itself. The Siglent SDS2000X Plus Series oscilloscopes provide a very nice feature, that is the power analysis option. So I will use this handy feature to measure the output noise of this power supply. The probe was a little bit loose, now it's okay. So let's go to the analysis menu and press the power analysis, then turn it on. There we go. Thank you very much. Now if I touch the signal part here and then select the connection guide, we can see a sample circuit that shows where the probe should be connected. This is actually a flyback converter, but doesn't matter. This is just a general guidance that shows you where the probe should be connected. So as it says, you should connect the probe to the output of the power supply, which I've already done that. I have digitally zoomed the screen, so the quality is a little bit low. You may have not be able to read the numbers correctly. However, it says around 9 to 10 millivolts peak to peak. I think the real noise is lower than this. In the next step, After I've done all of these experiments, I will move the camera forward and I will capture the oscilloscope screen clearly. Now what I'm gonna do is to connect a load to the power supply, and let's see how much is the output noise with the connected load. So let me remove this resistor. And mount a powerful resistor, this 4.705 watts resistor. A terminal block connector allows you to connect wires and loads such as this resistor easily. Let me close this terminal screw. Okay, the resistor is connected. Now I will play with the current limit and set it on 1 amp. So we will test the output noise under 1 amp load. Then I put the probe on the output terminal to measure the noise. Exactly like when we were measuring the output noise under no load. So let's see how much is the output noise under 1 amp load. It says around 9 to 10 millivolts peak to peak maximum. So we see no increase in the output noise even by adding a 1 amp load to the output. In the next step, I will move the camera forward and just capture the oscilloscope screen so you can see these numbers clearly. Alright, now you can see the oscilloscope screen clearly and sharply. I haven't touched anything, so the load is connected and it draws around 1 amp. One important thing I forgot in the last experiment was to limit the bandwidth of the oscilloscope. That was the reason I was receiving a lot of high frequency noises. So I should go here and limit the bandwidth to 20 MHz. Now I should play with the volts division knob and reduce the value. The jumps in the signal is because my hand shakes on the probe because I play with one hand with the oscilloscope. Now the signal is ready. Let's go to the analysis menu and select power analysis. From analysis, we should select the output ripple. We have these many options, however our output ripple is our favorite here. The connection guide shows a flyback converter. However, this is a tip for you, just to guide you where the probe should be connected. Anyway, let's come back to the main menu and enable the power analysis. And thank you very much. You can see the values on the screen. I really like when a device like this puts all necessary parameters in front of your eyes. Nice. When I limited the bandwidth to 20 MHz, as you can see, even the noise figure reduced because majority of the noise was not generated by the power supply. So this noise figure is quite acceptable for me. In the next step, I will talk about the circuit, PCB, components and component libraries. Just stay tuned. Alright, welcome back. This is the last revision of the board. It is a 2-layer PCB board and all component packages are 2-hole. In this revision of the PCB layout, I have added 2 more components that are C4 and R4. Do you remember that 4.7K basic load resistor? Now I have included that in the PCB layout, so you don't need to use any external resistor. The thickness of high current carrying tracks, such as this one, is 4.5 mm. For the schematic symbols and PCB footprints for this PCB also, I've used the Simaxis component libraries. Specifically, I used them for IC1, IC2, IC3 and Q1. So I did not waste my time to design these component libraries from scratch. And I feel comfortable with using these libraries because they are free to use and they do follow industrial IPC footprint standards. To install and use the libraries, you have 2 options. You can either go to the componentsearchengine.com and search for your desired components and import them in your favorite CAD software, or you can use the Simaxis CAD plugins and install your libraries using these plugins. Simaxis has provided plugins for all of these electronic designing CAD software in the picture. such as Altium, Proteus, KiCad, OrCAD, Allegro, Eagle, and others. I use Altium, so I use the Semaxis Altium plugin to install the libraries. This picture shows the assembled PCB board. The PCBs have been fabricated by the PCBWay company. The quality of the PCB's copper and the fabrication process are just perfect. I strongly recommend you not to go for cheap PCBs just for saving a few dollars, because definitely you pay the penalty in quality. Low quality PCBs are really annoying. Forget about them. Alright, you can find much more details such as schematic analysis, bill of materials, and much more details in the article. So just please visit the article link in the video description. Alright, the component search engine.com, as it says, it gives you a free access to schematic symbols, PCB footprints, and 3D models. Also, you can check the component prices and purchase them from the known distributors. Before I type the component name and show you how it works, let me see what it provides in the home page. Find the electronic component, download it for free, blah blah blah. It supports all of these electronic designing CAD software, newly added components, and most popular components. This is a very handy information for some purposes. Raspberry Pi, LM358, LM324, yes, of course, this STM32-bit microcontroller, yes, I'm agree, they are quite popular. Anyway, let's search for one of the components in our project. This MOSFET is very important, and there are many fakes in the market, really. For this MOSFET you have to be careful. So let's search and let's see what we can find. Alright, this is the search results. From the search results, I think this one is the best. Let's click. So it shows the manufacturer, some a brief description. MOSFET N-Channel, 60 volts and 50 amps. This is the schematic symbol. This one is PCB footprint, and this one is 3D model. Okay, you can download the datasheet here. The price in the Mauser and arrow have been already provided. You can click this and go to these distributors and purchase the component, and also you can click here. Before that, you can download the datasheet. The link is provided here. Anyway, check stock and prices. Let's see what it handles. Alright, this is a price in arrow, DigiKey, Vertical, Avnet, Funnel, RS components, Mauser again, TTI Europe, yes, TTI, TME electronic components. This one, element 14, network, okay, Avnet Americas. Anyway, if you click on any of these, you will go directly to the distributor and you can purchase the component directly. And all of this information are provided for free. Really, it's a nice website. I haven't seen anything like this before. So bookmark this website in your browser and have fun. At the end, let me add something. If I show you the distance between the electrolytic capacitors and the power resistors in the middle, If the camera get focus, alright, you will see there is around 1 millimeter or a bit more of distance between these components. I have increased this space in the last revision of the PCB, so you shouldn't be worried about this. Also, I recommend you, if you want to use this device continuously in high currents, please use bigger heat sinks and think about the ventilation. Okay friends, that's it. Don't forget to share and subscribe. Also, give me a big thumbs up. Catch you next time.